All right, so let's now look at what it means by differentiability of a function. And so at our level here, to begin with this topic right here, I have to make clear that at our level of learning about calculus, we only learn just about enough to understand about differentiability. But it's going to have to take an entire separate course in real analysis to clearly and fully understand that concept of differentiability here. So we only need to understand enough and good enough for us to do a lot of problems. That's all there is. So to start out with the concept of differentiability right here, let's look again at the way how we define how we can find a derivative. So let's say f prime, or I am going to start out with any given function. And then we start out learning the derivative at a given point. And so a here is a given point. And so we've learned through the limit definition that the limit of the function f at a given point a right here is found by f of a plus h minus f of a divided by h. And we take the limit as h goes to 0. Then, not too long ago, we came to a more general formula. So f prime of x here is our derivative of the function, the general derivative of the function f of x based on at any x input value. But it's the way to find that. And as a definition, it was also found by using the limits definition. So we're looking at f of x plus h minus f of x divided by h, and we're taking the limit as h approaches 0. So ultimately speaking, any of these work to find the derivative heavily relies on the concept of taking derivative. Taking limits. And so at this point, limits, if we recall from limits, there could be times where any of these limits could fail, or in other words, being a non-existing limit. And so if you look back at a little more closely and more formally from many textbooks, then any of these derivatives here only exist if the limits exist. Okay, so we only have that derivative at a specific given point if our limit process here turns into a finite existing limit. And same way with this, we got through with that lecture studying about the derivative as a function, and we came up with a way how to find a general derivative of any function. But now one thing to really emphasize, any of our work there is only possible if this limit work exist. Otherwise, if any of these limits unfortunately does not exist, then we wouldn't even have the general f prime, or we wouldn't even have the f prime at any specific given point. And so now I'm going to define what it means by being differentiable. All right, so here's our formal definition. All right, so the function let f of x be a function, any function that we're attempting to find the derivative, then the function itself is said to be And now I'm going to start using that formal term here. So f of x is said to be differentiable at x equals a. Okay, so that's one term right there. The function is said to be differentiable at this given point x equals a. If the work that we're doing f prime at a, and of course that work, the derivative, finding the derivative of f at a specific given point, that work is being done by taking the limits of f of a plus h minus f of a over h, letting h go to 0. So the function, once again, let me restate it as one statement right here. But f of x, our function, is said to be differentiable. So this is a property, this is an adjective right here, to be differentiable at x at a given x equals a if this limit works. So primarily speaking, we're focusing on this limit work right here. If this limit worked is an existing and finite value. All right, so having a little bit closer look into this, then, because the point of what I'm trying to point out now is that there will be times where we are attempting to set up the starting point, but unfortunately the limit does not exist. And so if that case happened, the limit of this setup does not exist, then in that way we're going to say that our function is non-differentiable. And so here, back to this definition, the function is differentiable at x equals a. It's a term it's a property we refer to this function. But that only happens when our limit work is successful, having an existing and turning into a finite value. Okay? And so along with what I just said earlier, let me switch to the other board and give that optional term like that. So in that way, now we can understand that if this limits f of a plus h minus f of a divided by h, and taking limit as h approaches 0, if this limit does not exist, or not finite, any of the case happen. Either we running into a non-existing limit, or we run into like an infinity limit, or not finite limit. Not a finite value. Okay, then f of x is not differentiable. Okay, at x equals a. So it's just a natural consequence of, as we based on our definition on differentiability here, our function f of x is said to be differentiable at a given point provided this limit here exists, and being a finite value. And so on the other hand, that means when we are failing to find an actual limit, when this limit runs into a DNE, and in our study at least, hopefully that anyone viewing this video at this point is well understanding what it means by having a limit does not exist, or having a limit being not a finite value. So any of the case here happens, then f of x is not differentiable at x equals a. Okay, and so along in that way right here, you can understand now that in the way how this definition is pointing out, then differentiability here that we're learning is the property that happens at one point. But then we can also extend that concept of differentiability for an entire interval. And so now I'm going to provide another definition. Now, save me some time by erasing everything and rewrite everything from scratch, because most of the next definition I'm about to write right here is going to be quite the same with this one. So I'm going to say let f of x be a function. And now the function f of x is set to be differentiable, but instead of being at a point in an interval from a to b, an open interval from a to b, if this limit, okay, is an existing and finite value, but for every value a inside of our open interval value x inside of the interval from a to b, in between a to b. Okay, and so this is how we can guarantee that some function is being differentiable, having a derivative anywhere in that interval. So differentiable at this point here means the function has a derivative. That's the simplest way of pointing that out, because when this limit fails to have a finite value or fail to have a limit at all, then we're gonna say that the function does not have a slope value, does not have a derivative value. Okay, and so of course right now up to this point, when I finished introducing the definition, it's still very unclear. But now we're gonna start out with doing a few examples right here, and along with what I said earlier right in the beginning of our video lecture here, then it's going to take a one formal course, and that course there is for the the undergraduate students, but in the junior level right there, to completely understand the concept of differentiability. And at our level here, since we're quite beginning into our calculus study, we're not going to focus on the kind of problem where we're going to have to prove whether a function is differentiable inside the entire interval or not. We're not going to be worrying about that kind of problem. But it would be actually more fascinating for us here at our level, at our beginning level, to do the kind of problem where we track down where the function fails to have differentiability, where the function would fail to be differentiable at a certain point. That is actually the kind of problem that we are able to do at our level. And so it's a little bit counterintuitive that we learn about differentiability, but we're not applying that to directly prove function to be differentiable everywhere in an interval or being in its entire domain. That's not simple for us to do here at our level, but we can actually do the kind of problem where we can track down and detect where the function fails to have a derivative, where the function is not differentiable. Okay, and so in that way, allow me to show our first example here. So I am going to call that example 1. All right, so in our example 1, we want to show that this function f of x equals an absolute value of x. Okay, we want to show that this function is not differentiable at x equals 0. And I have to also admit that I lied a little bit about we learned to detect, but actually the kind of problem we do in here, somebody already detects for us that this point right here for our function f of x equals absolute value of x. We already know that we already given a point that here we just want to prove that this function will fail to have a derivative at x equals 0. So we don't even have to detect anything. And that's what my point is. So we simply just have to be able to prove or to point out how this function will fail having a derivative at x equals 0. And that's all it needs. And so, and like I said, when the problem becomes more advanced, that's going to wait for when anyone viewing this video become more advanced in terms of calculus study. Right there. Okay, so I'm going to need to erase my other board because it is going to take quite a few steps right here. But so, long journey start out with always one single stepping stone right here. So our first stepping stone for this problem, doesn't matter if we're proving it's differentiable or not differentiable. We have to start out by setting up our work to find the derivative. So think about at x equals 0, then what would f prime, and I'm not saying that we know already whether we had an f prime value, we don't know. If we are, but if we would be finding it, then we would have to set up this formula. F prime of 0 would be, for sure, equals to this limit f at 0 plus h minus f at 0 over h. And as I'm saying, we don't know if we had an answer to this limit, but if we would be finding the derivative of this function at x equals 0, we would need to go through this limit process. Okay, and so yes, at this point right here, we have our freedom to go ahead and set it up into the function. So our function here is going to be, now f of x is absolute value of x, and so f of 0 plus h here means we're looking at absolute value of h. Remind yourself, the function is the absolute value function, and what we're looking at here is 0 plus h is h minus absolute value of 0. This here comes out from f of 0 plus h minus f of 0. And we're dividing by h. We take the limit as h go to 0. And of course, we're still tracking down the limits problem right here. We're not making any conclusion yet about whether or not we're having an existing limit or not. So we're just about working out the steps so far. But now absolute value of 0 is 0, and absolute value of h minus 0 is the same as, so here I'm looking at absolute value of h over h, and divided by the limit of h goes to 0. Okay, so throughout our class time together, I did have a challenge problem for anyone, especially students directly in my class. This current quarter, or the being in my class for any quarter, this used to be a problem where I actually challenged my student either as an in-class discussion or as an online forum discussion right here. But you should already expect an answer to this. But now in case of, but for a viewer in general out there, if you haven't seen how we can prove this, so I'm going to tell you, this limit here does not have a limit. Why is that? Because into my next board right here, the trouble comes starting out. The trouble all starts because we have that h here, but being in absolute value, and our limits here, limit laws. If we apply directly limit laws, first of all, we are not sure about absolute value of a limit, and we didn't have a direct laws about plugging a limit into an absolute value. So the safe way algebraically, recall for yourself, doing any limits. When we get stuck in algebraic techniques, the limit laws does not help. We're going to go back to breaking it down to a left-hand side and a right-hand side. So I'm going to put a pause on this. I'm going to hold on to that. Now I'm going to consider the limits for absolute value of h over h. But now considering when h approach 0 from the left-hand side, okay? But h approach 0 from the left-hand side, this line right here is quite critical. If h getting close to 0, but from the left-hand side, that means in the end all the value of h that we're choosing, that we're getting close to 0 have to be less than 0, negative value, because h is coming to 0 from the left-hand side. So here, make a note of that. That means all the h value is less than 0. But being less than 0 means further that if h is less than 0, then our absolute value of h can be rewritten as minus h algebraically and divided by h. And we take that limit as h approaches 0 from the left-hand side. And so with this work right here, minus h divided by h gives me a negative 1. And we're looking at limit as h goes to 0 from the left-hand side. And now limit law is going to start kicking in right here. Doesn't matter which destination point we're approaching for h right here. So h is getting close to 0 from the left-hand side, but our constant consequently turn out from the way it is here, then we are heading to a negative 1. And so this function here being a constant function, so our final limits for that is negative 1. That is the left-hand side limit of this function. And then we're going to reconsider. Same function, absolute value of h over h. But now we want to take a look at the limits from the right-hand side as h is getting closer to 0. Okay? And so once again, it's all the entire reason that leads to all this trouble, that breaking it down to a left-sided limit and a right-sided limit, simply because we cannot apply immediately limit value. The limit laws is right here in this step, so we have to put a hold on that and then start considering the two-sided limits. And so now, going with the going on for the right-sided limits here, then make note further that if we're letting h coming close to 0, but from the right-hand side this time, that means that our values of the variable h has to be a positive value. Okay? So taking account that h being positive value, in this case right here, when we're taking this right-sided limit, then this expression, absolute value of h over h, the absolute value now can get out of absolute value. So the h there can get out of absolute value, but we don't need to put the negative sign there. So it's simply just h over h. So I highly encourage anybody, if you're not familiar with how we can take an expression outside of its own absolute value, go back and review the algebra right there. Because we need that, your solid understanding of the algebra in terms of getting an expression out of your absolute value in order to move on and understand further. But now this limit here, once again I'm just rewriting it, getting close to 0 from the right-hand side. And now since there are no negative here, h cancel with h as common factor, we're looking at our final problem here becomes a limit of the constant function 1, and we're taking limit as h approaches 0 from the right-hand side. So this limit here is according to limit laws that we've learned, limit of a constant function. So now it turns into 1. So now what have we just discovered? Left-hand sided limit came to negative 1 as h approaches 0 from the left-hand side. But the right-hand side limit came to limit positive 1 as h came to 0 from the right-hand side. So in that case, left-hand sided limits result did not agree with the limits from the right-hand side. So in that way, now clearly speaking, this limit problem here is a non-existing limit. It's a does not exist, DNE. And so in that way, so now it's not only a limit problem, what is the impact, what is the consequence of proving this limit here to be non-existing? So now allow me to erase all that steps. Hopefully you took note, but as you have come to showing that this particular limit that we were setting up in the beginning, now known to have non-existing limits right here, fails to have a limit. So now back into my other board right here, our final conclusion. So therefore, in that way, therefore, the function f of x being absolute value of x is the term now for that not differentiable. Or maybe I wrote a little too closely right here. It's not differentiable at x equals 0. And this is the end of our proof. Okay? In case I haven't mentioned before in any of my earlier video lecture, for students who do plan to go into a formal math major and start getting into this habit, the end of any proof, we use this big square, but it means a period, a huge, giant period, meaning it's the end of the proof here. Okay? And so in this problem, we have just now proven that this particular function, f of x equals absolute value of x, does not have, being not differentiable at x equals 0, or in other words, it does not have a derivative at x equals 0. So we can't find it. If anyone is asking you, hey, find f prime at 0 for this problem, can't find it. It's a non-existing derivative. Okay? So along that way, let me point out a couple more proving problems where a function would fail to be differentiable. So let's look at example 2. And pretty much the exact same kind of example. So allow me to retain a few writing steps on the board here. So now the next one I have in mind here. So what about our function being f of x being a piecewise function? Okay, so we're looking at minus 2x plus 3. So the function f of x is defined as minus 2x plus 3 for if x is less than 1. Okay, and it's going to be x squared. So the same function would be defined as x squared in the other piece minus 2x, but only if x is greater than or equals 1. Okay, and so now we want to show that this function defined, piecewise defined right here, is not differentiable at the given point here. You can quickly make a quick good guess right there at x equals 1, because you see, natural sense telling us that this function has a break. And a break, it switched from one piece of function into using the other piece of function. And that break happens right around this value x equals 1. So everything was negative 2x plus 3. We would use f of x equals negative 2x plus 3 to evaluate the function if we choose input x less than 1. But then when we choose, any time that we start hitting x equals 1 or above, then we have to switch over. See, that's why I'm saying we got a break. We break from x less than 1 to x greater than or equal to 1. So now that behavior, we want to prove that this function is particularly not differentiable right at that value x equals 1. Okay, and so having some experience through the earlier example, let's have for ourselves that starting point again. So the whole point here is we're trying to show that our function here would fail to have a derivative at x equals 1. So that means we need to start setting up that derivative at 1 calculation. And let's see if we, after our limit process, if we can have a successful limit or not. And so if we would find f prime at 1, that means we would definitely need to, and as a safe work, f of 1 plus h minus f of 1 divided by h, and take the limit as h goes to 0. Okay, and this is even going to produce such a nightmare for us right here. We don't even have one particular function to start substituting this 1 plus h expression in there, and that's what the problem is. Okay, and so now allow me to do this. we are going to get directly into considering the two-sided limits. So on my other board right there. And like I said, the whole reason that I have to directly get into the two-sided limit simply because with our function being as such, with our function being piecewise and broken into two pieces like this, we don't even know how we can plug this, because at this point, the way how I see it, we don't know how we can see this as greater than 1, that expression, or being less than 1 or not. And so in that way, we have a difficult time choosing. And so now it's to make it really clear and crystal clear, let's break it down to two-sided limits. And so left-hand side limits, okay, I am going to consider the left-hand side limit. And so just write the general notation here. I'm going to find the limit as h go to 0 from the left-hand side for this function. F of 1 plus h, for this difference quotient, f of 1 plus h minus f of 1 divided by h. Okay, and so if we're letting h going to 0 from the left-hand side, think about it. Make a quick hand sketch of the table a little bit. Okay, so the point of the 1 plus h here, think about the 1 plus h a little bit. But if we go negative 1, that's on the left-hand side of 0, and then negative 0.1 and negative 0.01. and negative 0.001, for example. Okay, and so if this add with an, so this is h right here. Okay, if h plus with 1, we got a 0. This value is less than 1. Okay, if we have a negative 0.1, that's for h, and plus 1 right here, we're looking at a 0.9, which is less than 1. And I'm not really doing limits here. I'm just trying to, and wait until I finish a little further with this table and you will understand what I mean. But then as h, when h becomes negative 0.01, which is closer to 0, but everything I'm doing here is on the left-hand side. Okay, we're looking at 0.99. This is also less than 1. Okay, so my point is, or maybe if you're picky, any viewer right there being picky, you're gonna worry, how come I didn't finish that? Okay, then we can finish that. Negative 0.001 added with negative 0.001 added with 1 right here, because h here is these are these values. So, but this column right here is h plus 1. So 0.999 here is in the end still being less than 1. So my point now is that we can legally use, you see what happened if our input is being less than 1. If our input is less than 1, then we have to, because I just proved it. I just proved that if h is getting close to 0 from the left-hand side, then consequently any of these value of the expression 1 plus h have to be less than 1. And so in that way, now I am going to clearly indicate that as far as f of 1 plus h, it is going to become minus 2 times 1 plus h plus 3. So that's f of 1 plus h. Okay? But now minus f of 1, be cautious here. F of 1 is indeed, one more time, let's review our function. The other condition does take that possibility when x equals 1. So in other words, if you substitute x equals 1 into the function, we have to use this bottom piece here. And so in that way, now for minus f of 1, I have to go with 1 squared minus 2 times 1, okay, and divided by h. All right. And so, and we'll take the limit as h goes to 0 from the left-hand side. Okay. And then now let's work it out further. All right, so minus 2 minus 2h, okay, plus 3 minus 1 plus 2. Lots of cancellation can happen here. Okay, so we have that cancel with this 2 right here, and we have these two combined like term and over h right there. Okay, and this h goes to 0 from the left-hand side. Okay, and so this is going to give me So minus 2h plus 2 over h. H goes to 0 from the left-hand side. All right. And so that is going to be now. So at this point, I have to admit a little bit that my approach for this particular problem is a little unique in terms of not too many professors out there delivering the concept of differentiable like how I deliver for now. And so what I need to recall for anyone viewing my video is that at this step right here, we're still not quite safe to use the limit law directly. So in order to make our final conclusion on this limit as h goes to 0 from the left-hand side, let's algebraically break it down even further. Now, minus 2h cancel with h leaves me a minus 2. But that term here, cancel the term with that h, we're looking at 2 over h. And now we can take the limit as h goes to 0 from the left-hand side. Limit as h approaches 0 from the left-hand side. And so now limit laws are going to start being able to apply here and gives us some answer here. Now first term gives me a negative 2. But the next term right here, let me write a little scratch work, but we've had since our beginning of the quarter in one of my video lecture, I pointed out that this particular limit right here as h goes to 0 from the left-hand side is a negative infinity. And you can go ahead and review our earlier lecture right there. But now, how does that help into this problem? So for this particular term, yes, we have a constant 2 here. But think of that as a 2 times a 1 over h. And so when the limits as h go to 0 apply with limit laws into that term, then we're looking at minus 2 plus with negative infinity. Okay? And so in the end, negative 2, but plus with negative infinity, something fixed but added with something that keep growing to negative infinity. Our overall answer here, our overall limits on the left-hand side is a negative infinity. So that takes care of the left-hand side limits of our particular derivative problem. So now let's switch our attention over to the other side. And yes, one problem might take you quite some time to get through, but then at the end, I will get back to the problem and give some better explanation and point out a couple other useful things about this problem. So on the right-hand side, approaching the same limits right there, and let me remind anyone viewing the video, but we started out all the way from trying to prove that this limit here does not have a limit. But then right from here, we couldn't use the limit law. We didn't even know what to do with this function. So we have to break it down to left and right limit like that. And so we already took care of the left-hand side limit, and it came on the left-hand side. This particular limit here came to negative infinity. So what about on the right-hand side? Okay, so our function here, breaking it down, f of 1 plus h minus f of 1 over h, but taking limits as h goes to 0 on the right-hand side. Let's do a little bit of scratch work again. H coming close to 0 from the right-hand side means we can try with 1, then positive 0.1, then positive 0.01, then positive 0.001. And we're not really finding limits for this table. We just, as h, these are the values of h that I purposely kept on the right-hand side of 0. And so if we plug these values into this expression 1 plus h, then we're looking at 1 plus 1 is 2, then here it's a 1.1, here is a 1.01, and here is a 1.001. But anyway, these values are all indicating that they're greater than 0. Greater than 1. Of course, they're greater than 0. I apologize for my mistake right there. But now what's useful about knowing this, that 1 plus h, as h getting closer to 0 from the right hand side, these values for 1 plus h are all greater than 1. That means for the function f of x, f of 1 plus h right there, now we can use our function will become, because when x is greater than 1, then we have to use x squared minus 2x to evaluate our function. And so in that way, now I'm looking at, or maybe I should write it in the next line like that. The long fraction bar 1 plus h all squared minus 2 times 1 plus h. Now I can legally approve that I have to use that bottom piece from my previously defined function. Then I'm going to subtract, and f of 1 is clearly we have to use the second piece. So 1 squared minus 2 times 1. Okay, and over h. We take the limits as h approach 0 from the right hand side. And then anyone at this point watching this video of mine has been quite hopefully fluent enough with factoring out, foiling out these perfect square right here. So I am going to FOIL out that perfect square, and I'm looking at 1 plus 2h plus h squared. The minus 2 distributes for each term, and be cautious for sign change. So minus 2 minus 2h. Okay, and then here we're looking at minus 1 plus 2. All right, and then there will be lots of term for cancellation. And here we're looking, limits go to 0, but from the right hand side. Okay, and 1 cancel with negative 1, negative 2 cancel with 2, plus 2h cancel with minus 2h. We're shockingly ending up with h squared over h. Okay, and take the limit as h goes to 0 from the right hand side. And so one more step for here, we can cancel out the common factor h in both numerator and denominator. And so in that way, our limits from the right hand side, limits as h goes to 0 from the right hand side, turns out to be, we simplify h squared over h down to that expression h, simply h. And so in that way, now this limits turn to 0. And so what have we found right here? And we have done a lot of work to the point now that we have to briefly look back a little bit. But so starting out with all this work right here, we didn't know how to substitute in that 1 plus h, so we had to carefully broke it down to the left hand side and the right hand side. So let's look back at this. But this same limits, but the left hand side, okay, limit of this f of x, 1 plus h minus f of 1 over h, but letting h get close to 0 from the left hand side, and we had a negative infinity. And then just now on the right hand side, just now we found that this is a 0. So the two-sided limits do not agree. And so in our understanding of taking limits, simply what I point out, the two-sided limits, left-hand sided limit came to limit negative infinity, whereas right-hand side limit on my other board came to limit 0, as you hopefully already took note. And so in that way, it's apparently now proving that this overall general limits, when h gets close to 0 from both sides, this is a does not exist limits, because the two-sided limits just simply do not agree. And so now at this final statement right here, we are now ready to make our conclusion that now at this point I'm going to be saying therefore as a proof. So after we've done showing a lot of steps right here and putting all the pieces together, then therefore this function, okay, and I'm using that term again, this function f of x is not differentiable at x equals 1. And what I said a little bit earlier before I finished with this problem was that my style of approaching this problem a little bit unique compared to many other professors out there teaching this, because I just want to approach proving this function failed to be differentiable at this given value completely based on its own definition and nothing else fancy that I brought in. So consequently, I had to bring back a lot of limit work for us, which, you know, some of you might feel the hesitating doing limit work, but it's actually extra practice that I intentionally put it here for any of my viewers, and especially students who are really enrolled in my class to keep, you know, working and become more flexible and more sharp in terms of finding limits like that. And then allow me to finish with some other example, and then I'm going to come back and give a better explanation of how this work here can be quickly proven to be not differentiable. Okay, but that was our example 2, and we did a proof. And then with that proof, now this is the end of the proof, and once again you can start taking that new symbol here, indicating it's a big huge period, indicating that we're ending our proof here. All right, and so now let's look at our third example. Let's look at now example 3. And we want to show that, again, we want to show that our function f of x equals a cube root of x. Okay, we want to show that this function, and I do believe that throughout pretty much in my entire lecture so far, we haven't done anything that involves the cube root. So let's give it a try. Okay, so we want to show that this function, the cube root of x, is okay, and the ultimate statement here, we want to prove that it is not differentiable. Okay, differentiable at x equals 0. Okay, and once again, the famous starting point is if we would be finding the derivative of this function at 0, if we would be finding f prime at 0, then we would need to do, as a starting setup, f of 0 plus h minus f of 0 over h. And this function is a little bit easier compared to our earlier function in example 2, in a sense that we already had the function only in one piece, and it's easy to substitute in that expression right there, that 0 plus h expression. But now, by the way, I still need to complete our expression, our starting setup, with that limit h going to 0. And so immediately in the next step, before I have to move out to the next board here, we can quickly see that this is cube root of h minus cube root of 0, and needless to say, cube root of 0 is 0. So that's getting it ready for the next step. Okay, over h. So that came straight out from our starting setup, the difference, the famous difference quotient here. And of course, we need to take the limits to as h getting close to 0. And so how about one more step can be written here in this board. But so what I see here is that we're looking at cube root of h over h, and we're letting h comes close to 0. Okay, and so now for this kind of problem, we actually don't even need to break it down that far into the left-sided limit and the right-hand-sided limit. And let me point that out in our next board space here. Okay, so let me bring everybody into my next board. But so right from the previous step, cube root of h over h. Now remind yourself that cube root of h is h to the 1/3 power. Okay, h to the 1/3 power. And so in that way, Okay, and after that consideration right there, then this limits problem we can, once we understand the nature of cube root of h, we can, there's some common factor. So cube root of h does cancel with h, and that becomes 1 over cube root of h square in the denominator. Okay, and we're taking this limit as h goes to 0 from the right hand, I mean from generally from both sides. All right, and so you can have your freedom to quickly try this on your own. If we try a separate 1 over cube root of h squared and take limit as h go to 0 from the left hand side. Okay, you can try with table, you can try with the limit laws as well, but the answer for that is going to be a positive infinity. Okay, and the same way, the same thing that happens with the right hand side limits, this 1 over cube root of h squared here, as we take limits for h going to 0 from the right hand side, we also go into positive infinity. You can also use quickly use decimals to get the graph of this, and you can find out that as we are getting close to 0 from both sides, the graph is going to grow like this. And so in that way we have a conclusion. So this limit, it's not a finite number, but it does go into a direction. That direction is a positive infinity. But so now, sadly, I erased the definition we've had earlier, but in order for this derivative to exist, we need, in order to say that the function is differentiable, then we need this limit to be a, number one, being an existing limit and being a finite value. So yes, back on my board, I personally see that this is an existing direction, but this is not a finite value. So in the end, our overall limits here fails. Our function here, seeing that we have this limit turns into an infinite value, then we're gonna be able to make our final conclusion that that implies our function f of x, okay, is and it's all due to that fact right there. The limits, the entire limit setup, the limit definition did not run into a finite limit. So f of x is not differentiable. Okay, at x equals 0. Okay, but the reasoning for this, for being not differentiable, because this time instead of failing to have a limit, we do have a limit going to positive infinity. But that's the problem right there, because our limit goes to an infinite value, a value that's not finite right there. Okay, and so at this point, let me show the graphical interpretation of the three results we have found right there. All right. So allow me to bring up my function. Okay, so right here in our first example, example 1, this is our famous function for absolute value of x right here. That famous V shape, 90-degree angle right at that corner right there. And I kind of said the word corner. So here's the idea. You see, what does it mean by failing to have a derivative at x equals 0? Because we proved in our example through the math that this function, absolute value of x, failed to have a derivative at x equals 0. So think about it. I have my dragging point here. Think about if I would put my tangent point anywhere to the left hand side. See, x equals 0 is right here at that corner. So if I would put any tangent point on anywhere to the left hand side of x equals 0, then think about what the tangent line would look like. The tangent line is just simply this line pointing down itself right here. This line, this piece of line, this half line right here itself. So the tangent line would have the slope being -1 all the way through until we hit anywhere really close. But when we really hit x equals 0, really, anyone can tell me, anyone viewing this video, can anyone viewing this video tell me how we would put a tangent line when x really hits 0 right there? When x equals 0, is the tangent line going like this? Or is the tangent line going horizontal? Or is the tangent line going like the other line? Nobody knows. And that's how it's indicating. And then and further observe that if we switch to the right hand side of the curve right here, the right hand side of the curve, and then from anywhere I put my tangent point now, then the tangent would look, the tangent here, anywhere here would have a slope being +1. So that clearly shows that right at 0 we fail to be able to place a tangent line there. Okay, and so right here, make notice that the example here, graphically speaking, we have a corner. When our graph produce a corner like this, or like a sudden turn, a corner, or another way of saying it's a sudden turn like that, then we're going to have our function being not differentiable at that point, at the point where the function is having a corner. So that brings up one of the cases right there for being not differentiable. All right, so and what I meant by corner, see, so generally speaking, you have a function and the function create a sharp turn like this, a sharp corner like that at x equals a, which our graph for absolute value of x fell into this particular criteria right here. We have a sharp turn, an angle, a corner right here. Then this is where we have not differentiable. And that's why, I mean, simply looking at the graph, then of course sometimes people can debate, how do we know if it's a sharp turn? How do we know if it's an angle, a corner? That's why we had to tear it down and doing the math, the formal limits work right there. And the limit work obviously show that left hand side and the right hand side did not agree, come to different slope value. Okay, and now again, on to example. If we're looking into the other example, and let me quickly bring that up right there. All right, so here we go, our other problems. Now let me put it on screen right here. All right, so ladies and gentlemen, this is our piecewise function that we used in our example 2 right there. So this piece right here, when x is less than 1, and that's why we had an open point right here. And when x is less than 1, then our function here, let's check for consistency, but minus 2x plus 3. 3 is the y-intercept, minus 2x was the slope, -2 right here. So this is minus 2x when x is less than 1. And then the solid point stays on the other piece, and the other piece looks like it's a quadratic function right here. Okay, so when x is greater than or equals 1, then we have this, our function was x squared minus 2x. And so that's the graph for our function. And so, all right, so now think about if I would put if I would put a tangent point anywhere on the left piece right here. Okay, anywhere on the left piece, then if we stay anywhere on the left piece, then we would have some kind of slope, but then we don't know what happens right when it hits to that point right here, because first of all, that point is empty on the left piece, and that point is here. And so tangent line would have a slope if we were strictly to the left. Okay, but when we hit to x equals 1, we don't know what that tangent line is. And then when we switch to the other side right here, okay, and let me now switch to the other side. Okay, if our tangent point switch to the other side, even though if we can stay right here at that point, but then we don't know what's on the left of that. And then if anywhere here, then we would have a positive known slope. Okay, and so in that way, and further in our term that we already learned previously, then this function is discontinuous. Okay, this function is discontinuous right at x equals 1. So it actually will bring up something. It has a jump right here. Okay, and so now I'm gonna clear out my board. So this problem we already proved in the example, through the example, that it was not differentiable at x equals 1. But now investigating the graphical aspect of that, then it had a jump. So now we can generally make a conclusion that anytime that our function has a jump, say at a value, it's going down one way and it jumps to another piece right here, that for sure will be at that breaking line right here, x equals a. Then our function is also not differentiable. Okay. And then having a jump right here also means the function, if we notice, the function is not continuous. Okay. The function is not continuous. And so along with what we have recognized here, allow me to bring everyone into the next understanding that I'm going to need to move over to my other board. All right. So there is now, because we can, after example 2 and now seeing the actual graphical explanation of example 2, and it pointed out a generality regarding how, having jump in a function and how it's related with differentiability, then there is actually a theorem. And now I can start mention that theorem, and that theorem will become handy for us. Okay, so here's a theorem. And our theorem says if f of x is differentiable, okay, at a value x equals a, then that consequently means that means f of x is continuous at x equals a as well. Okay, so being able to place a tangent line, being able to have a derivative at this given value, that's what differentiable means. So being able to obtain the slope of tangent line at that value x equals a, that also means, that implies automatically that our function will be continuous. You can draw the graph through that point x equals a without lifting your pencil. But so this theorem right at first sight doesn't give too much understanding, but if we look at the logic the other way around, if f of x is differentiable at x equals a, implies the function being continuous, then there's the opposite logic to think about. Now that also means and this is logically equivalent. Okay, this also means as a remark. And let me switch to a different marker. If for any reason that we can find out if f of x is not continuous, if we can prove that f of x is not continuous at x equals a, not continuous at x equals a, then f of x can further be implied, be concluded that is not differentiable at x equals a. Okay, so I had my reason for not mentioning this first, right in the beginning after I mentioned the definition of differentiability. The whole reason was because I want anyone studying differentiability with me here would be able to just simply prove differentiability or prove non-differentiability immediately right out from the definition without knowing too much extra information. And now with this extra information being added on top, of course, when I'm saying extra, that's only mean for our level of learning here. But when you go to a more advanced course in calculus, or particularly your junior year math major, the real analysis course, for example, then this theorem is actually one of the very useful theorem. It's just for us here, being just only the beginning calculus students, then we haven't been too far in math yet. Then I call this the extra information, because it makes things better, but you don't see much usefulness of that yet. But so now let me point out quickly how useful this theorem can be applied into one of our examples earlier. So now let me erase my other board. So back to that example 2. We are not exactly reinventing the entire example, okay? But I would just say back to example 2, and we're going to look at that in a different way a little bit. But our function was f of x equals minus 2x plus 3 for x is less than 1, and then x squared minus 2x for x is greater than or equals 1. So I'm just pointing out that we wanted to show that this function is not differentiable, okay, at x equals 1. So the plan here is that once we learn about that extra but very, very nice result right here, if the function is differentiable at a given point, then it must be continuous. But the opposite logic of that here means if we can somehow prove that the function is discontinuous, not continuous, if we can prove that our function is discontinuous at the given point, then it will consequently imply that our function is not differentiable at the given value. And so why do I mention that here in this example? Because we have learned the skill in our earlier lecture. We can easily, anyone viewing my video here can easily prove that this function f of x is discontinuous. So I will actually leave that for readers and viewers for my video here. But the plan here I can point out as a plan. We can prove that, or we can show that this function f of x is actually discontinuous at x equals 1. And so you take your steps, prove this, and then this is actually extremely easy, and that's why I feel confident to leave that for viewers to prove that on your own, and go ahead and pause the video and make, get paper and pencil out and prove for yourself. And once you prove that result, and all of you viewing my video here agree on that this function is discontinuous at x equals 1, then our ultimate final conclusion here, we can just simply say, hey, so in that way f of x must be not differentiable at x equals 1, and end of the proof. Okay, so of course I apologize that I didn't go this way earlier, but like I said, I want in my philosophy, I want anyone who learns this, who study differentiability with me, to be able to prove a function being not differentiable but entirely based right out from your beginning definition without any extra understanding. And now with the extra understanding, then you're going to start appreciate how useful that extra understanding that you have learned, okay, will become useful for you. Okay. And so now, one more time, let's look into our case for example 3 graphically. All right, and so let me quickly prepare that graph on my screen here. Okay, and now I'm gonna need to also write a lot of things on the board, so allow me to also erase my board here. All right, so graphically speaking, now let me show everyone the graph of our cube root function in example 3. So there you go. This is the graph for f of x equals a cube root of x. Okay, and so this time, so we said we concluded in the example that we did not have a derivative at x equals 0. X equals 0 is right here. Okay, x equals 0 is right here. I'm trying to make my best to get that. Okay, and so x equals 0 is right here, and I'm trying to make some snapping. All right, and so what exactly does that mean by? I'm gonna need to do a little more adjustment. Okay, so now I can move my points a little easier. Okay, so we saw through our work that the limits turn into a positive limit. Okay, so let me get back to the board here. We have done this. Our f of 0 plus h minus f of 0 over h, and taking that limit as h go to 0. And of course, this function here, our function was f of x equals a cube root of x. And we came to this limit as being a positive value. Okay, being a positive value. And of course, all that here is to look for the derivative, the slope of the tangent line at x equals 0. And so you can see that I intensively keep mentioning the term slope of the tangent line, because as long as you stay right on that concept of the slope of tangent line, and a lot of things will get cleared out for you. Okay, so if you visualize this slope value, that if we visualize this derivative value as the slope of the tangent line, and try to imagine that tangent line you place at x equals 0 on the curve right here, that will explain a lot. So what does that mean by having that limit to become positive infinity, to the point that we concluded that the function was not differentiable, did not have a derivative at that point? So here's why. Okay, and so on our function, now I am really going, for this time graphically, I am going to put up the tangent line. So the tangent line is just fine. We can have any slope here, we can have any slope, but now observe the motion of my point here as I drag my tangent point closer to 0 and closer to 0. Okay, and maybe I'm gonna refine. All right, so you can see that what happens when we get closer to 0. The tangent line become more steeper, and to the point where it gets to, okay, and to the point where it gets so close to 0, then it's become a vertical line right here. Okay, and when it really hits x equals 0, it becomes a vertical line. That's the idea right here. And so vertical line in our algebra, understanding, a vertical line doesn't have a slope, and that's why. See, when tangent line become a vertical tangent line like this, you see, it's not like so the function is still continuous. Okay, and it's not like having a jump or anything like that. But when, for this particular case, when x equals 0, when we hit x equals 0, we are gonna obtain, our tangent line is still there. It's not like we don't have a tangent line, but our tangent line becomes a vertical tangent line. And vertical tangent lines mean we do not have a slope, or in other words, our slope is undefined. Okay, and so in that way, and actually I should have not said undefined, but now it just means when we getting closer, and as a limits concept, getting closer to x equals 0, then our slope become infinite because it's vertically straight up like that. Our slope of the tangent line is infinite. It's in the sense that it's vertically straight up. Okay, and so, and that's the reason why again, that when we have anytime that we have our limits problem right here, that the limits definition of a derivative turn into an infinite value, then we don't have, our function is not differentiable. Okay, f of x is not differentiable. But now graphically, we can use that to make judge that. So when the graph gives a sort of like a vertical situation like this, if the graph gives you a vertical tangent line, that is also another case where, see, x equals a is right there, and so that's where we have this function. So the function f of x is not differentiable, right, at x equals a, simply because we have a vertical tangent. All right, so concluding our discussion in this lecture right here, after all three examples, then my aim is to point out all three cases together graphically. All right, so when you simply just have your function being given as a graph, a lot of times, then if your function given as a graph produce a sharp angle somewhere, or a corner somewhere, or a sharp turn somewhere at a value x equals a that you recognize, that is where we have our function being not differentiable. Okay, and we have already seen that earlier. And then another case we can have is when our function come to a jump at x equals a. If our function has a jump, either with a solid point on one end, or no solid point at all, but that's also a case, and it's discontinuous. And being discontinuous, of course, our function will be not differentiable. Okay. At x equals a. And ultimately, the very last case that we just now investigated, when our tangent line, it could happen too, sometimes when the tangent line is vertically pointing up like this, being straight up like that, vertical tangent line, that is also when our f of x is not differentiable at that given value, x equals a.